So hello everybody and welcome. Thank you for joining us for the fourth SPHERIC Global Seminar on SPH. I've really enjoyed all the seminars so far. I'm enjoying having an opportunity to listen to some really interesting presentations and think about SPH and talk a bit about SPH every few weeks. The theme today is the SPHERIC Grand Challenges, which are 5 major areas identified by the SPHERIC community where SPH needs progress. Our speaker, Dr. Renato Vacondio, is somebody who has made significant contributions to several of these grand challenges. And he's put his work into practice in this area as well as a developer of DualSPHysics. He's implemented his ideas and shared them with the community. Renato is an associate professor in civil engineering at the University of Parma, and he organized the SPHERIC workshop in 2015 in the very beautiful city of Parma. We'll start in a moment, so please do keep your microphones on mute and keep in mind we're recording the seminar. We will have some time for questions and discussion at the end of the seminar, but we won't record that, or we won't publish the recording of that. Okay, Renato, over to you.
Okay, thank you very much, Nathan, for your nice introduction. As Nathan was explaining, this talk is going to be about the so-called grand challenges for SPH numerical schemes. So if we go back to the beginning, SPH was invented in 1977 to produce astrophysical simulations. And here on your left, you see an example of a possible astrophysical simulation done in the early 90s using just 3,000 particles. The same problem is now has been recently simulated with the so-called Swift code with 100 million particles. And so you see from the movie that the level of details and the quality of the results they are producing now is quite different from the one they were obtaining 28 years ago. If we move to free surface incompressible flows, more or less the same idea applies also there, because Joe Monaghan in his seminal paper of 1994 was simulating a dam break flow with a few hundred particles, whereas nowadays everyone or almost everyone is simulating free surface flows, very complicated, with interaction with rocks, as in this example, or interaction with other structures, coupling, and using several millions of particles. So it's clear that in SPH has made important progresses in the last years, but nevertheless, in my opinion, not just my opinion, SPH still requires important development to be adopted by academia and industry. And the idea of identifying 5 grand challenges is exactly going towards this direction, because we wanted to put some focus on topics that need further research. So those are the 5 grand challenges which are thoroughly discussed in a paper that we recently published on CPM. But in this talk, since I have only 40 minutes, by the way, I asked Ben to speak for 2 hours, but Ben and Nathan said that is not possible. So unfortunately, we have to restrict ourselves to just 2 of them. And I choose the grand challenge number 1 and grand challenge number 3. Before going to specific grand challenges, let me recap briefly recap some key ideas of SPH. I apologize if this is a bit boring for some of you. So why SPH is different from any other numerical scheme? Well, first of all, because SPH has two different sources of error instead of just one, has the classical Eulerian schemes have. The two sources of error of SPH are the smoothing error and the discretization error. The smoothing error is the one that is there at continuous level, where basically in this convolution, you substitute the delta Dirac function with the SPH kernel W. Can you see my mouse, by the way? Okay, thank you. And in order to reduce this error, we have to put H to 0. The other error is the error that you have in any numerical scheme, and is we call it discretization error, and is the one that appears when you have to approximate the integral with a summation. And so this means that your continuum is discretized with a certain number of points or particles. Okay, the second aspect that makes SPH different from other numerical schemes is the fact that it is Lagrangian and meshless. So Lagrangian means that particles which are used to discretize your domain move with the fluid velocity, and meshless means that those particles have no topological connection, and to make things even worse, there is no partition of unity in your domain. Or in other words, you don't know exactly where your volume or the particle volume is in your domain. Okay, so now if bearing in mind those information, we move to Grand Challenge number 1, which is convergence, consistency, and stability. First thing I wanted to say, recalling the so-called Lax equivalence theorem, is that consistency, stability, and convergence are not disconnected. And because the Lax equivalence theorem says that if you have consistency and stability, then you can get convergence. Well, strictly speaking, the Lax equivalence theorem is valid only for finite difference schemes, but here, I mean, at least I am an engineer, so for me is enough. Maybe for a mathematician is not, but who cares? We have problem to solve. So in any case, in SPH, there are two historical sources of instability, which are somehow connected. The first one is the so-called tensile instability, and the second one is the pairing instability. So the tensile instability, I think everyone who has run a few SPH simulation has experienced it. Tensile instability is when your particles clamp together and you will see large void in your domain, and together with that, some non-physical velocities and pressure. Looking at the paper of Swigger et al. In 1995, which they did an analysis using a von Neumann stability analysis theory, and they discovered that they discovered some interesting properties of the SPH interpolation. And so, practically speaking, if we restrict ourselves to fluids, this tensile instability appears basically when you have regions with negative pressure. Authors have proposed different solutions for that. The most simple one is background pressure, which doesn't work for free surface. Then Monaghan proposed another fix, which is adding an additional term in the momentum equation, which produces a repulsive force between particles, and this force prevents particles to clamp together. Morris et al. And later, in a slightly different way, Sun et al. Proposed to switch from the formulation of the momentum equation where you have a plus between the two pressure terms to the one where you have a minus. And this solved the problem of tensile instability somehow, but introduces another issue, which is related to the fact that you are no longer conserving momentum. So basically, none of those solutions is ideal, at least in my opinion, and all of them have advantages and disadvantages. But a definitive solution to that has yet to be found. Well, the pairing instability is similar, but slightly different to the tensile instability. You might have seen it or not. It depends how is the age over the X ratio you are using in your simulation, and also which kernel you are using. Here you don't see any unphysical velocities, but what you see are particles that are slowly overlapping pairs. But for that, I think there is an effective solution, as Den and Ali described in their famous paper, because if you use a kernel which has a positive Fourier transform, you are able to prevent this instability. In any case, in my opinion, in SPH, there is a dichotomy. And the dichotomy is between the fact that we want our scheme to be Lagrangian, because we want to take advantage of this property in order to describe free surface flows or multi-phase flow with very complex interfaces. And at the same time, we want our scheme to be accurate as possible. The problem is that if we are Lagrangian, it means that we are not controlling the particle position. And the particle position has an influence on the accuracy of your SPH interpolation. How is this? Well, Nathan, I think you are familiar with this picture. If we look at this picture, which gave me a lot of head cakes the first time I saw it, and this is taken from a paper from Nathan Quillan published in 2006. You see that here, Nathan did a convergence analysis, reducing the smoothing error by basically reducing the smoothing length of the kernel. And he was seeing that if particles have no disorder, no problem, you are getting the theoretical convergence rate provided by the kernel. But if particles are disordered, for example, if we choose a ratio between sigma and dx equal to 0.02, you see that you are converging up to a certain point, and then your SPH interpolation is actually diverging. And this is happening even before if particles are more disordered. This means that for a regular particle distribution, the SPH spatial interpolation might not converge at all. So this is telling me that it is very important in your SPH scheme to control the particle distribution. Okay, so everyone is saying that the fact that SPH is Lagrangian is one of the main advantages of the scheme, or not. Maybe not, because if we look at the literature, we see that all authors that have tried to simulate free surface flows with SPH, including Monaghan in his first paper in 1994, all of them are introducing some kind of correction to the pure Lagrangian motion of the particles. So maybe we don't want the scheme to be fully Lagrangian. The most extreme variant of those corrections was the one adopted by Linde Stansby in 2016, where they put 0 instead of the velocity to the particle update, meaning that the SPH scheme they proposed became Eulerian. And with an Eulerian SPH, they were able to achieve basically an arbitrary order of convergence, at least in space. For example, if you are using a fourth order Gaussian kernel and particles arranged on a Cartesian grid, you can get exactly fourth order convergence in your SPH interpolation. So the challenge is getting the same order of accuracy with removing the hypothesis, this extreme variant. A slightly less extreme variant is the so-called fiction shifting, where you don't keep particle fixed, but you add a small correction, which is delta here, to the Lagrangian motion of the particles. And the correction is computed as with this equation here, where I is just a non-dimensional coefficient, and the gradient of Ci is the gradient of the particle concentration, computed obviously with an SPH interpolation like this one. Okay, so physically, okay, this is the gradient of the particle concentration, but mathematically, okay, I'm an engineer, but sometimes looking a little bit to the math might be useful. So mathematically, this is nothing but the SPH approximation of the gradient of 1. Meaning that when we are doing this, we are trying to move particles in a direction that is giving us a better approximation of the gradient of 1, or if you like, to the gradient of a constant function. Okay, so in my opinion, this is a very good idea, but there are also issues related to the fiction shifting. The first issue is that the formulation is explicit, so there is no guarantee that the gradient of C is small at every time step for every particle. And on top of that, you are correcting the Lagrangian motion, or you are deviating from the Lagrangian trajectories, and this introduces an error. Okay, to compensate for the second issue, you can somehow correct physical quantities, even though people are not doing that anymore because it's expensive and they are assuming that or imposing that the correction is very small compared to the Lagrangian velocity. But there is still the issue, the first issue still remains. So in order to solve this, we went from normal shifting to super shifting, or iterative shifting, as Professor Stansby called it. And let's have a look at this super shifting idea now. So how it works? Well, in super shifting, particle positions are still adjusted using this correction, but we don't use it every time step. But we instead we activate it only when there is at least one particle which has a gradient of C that is larger than a certain threshold that we define at the beginning of the simulation. Then when this condition occurs, we activate the super shifting and we keep iterating. So we apply this correction many times to all particles in our domain until we are able to reduce the maximum value of the gradient of C in our domain to 10% of the initial threshold we choose. What do we get by doing that? Well, this is a movie with in a square periodic domain where particles are initialized with a certain level of randomness, and then we let the iterative shifting run for many iterations. And you see that by doing that, we are able to reducing the gradient of C a lot. So, for example, if we do some quantitative analysis on the previous simulation, we can see that by running 1,000 iterations, we are able to recover the same level of accuracy we can get if particles were arranged on a Cartesian grid. And if we push it further and we do a convergence analysis, doing iterative shifting or super shifting for every resolution, we see that we can recover exactly the same convergence rate produced by the kernel we are using. In this particular example, we are using a fourth-order Gaussian kernel, and so we were able to recover a fourth-order convergence rate. Okay, that is for just the spatial SPH interpolation. But if we take this iterative shifting or super shifting, and we plug it into an actual SPH solver for weakly compressible flow, what do we get? Well, here I'm showing you the result for the 2D vortex test case, where we can compare against an analytical solution. And this figure here is showing you the gradient of C, or the L infinity norm of the gradient of C. You see that if you are using the efficient shifting, it is constantly increasing. Whereas if you are using iterative shifting, every time you activate it, the L infinity norm goes down by an order of magnitude. But that's expected because we are controlling it explicitly in our scheme. If we look very briefly at the density error, we see that if we are using the efficient shifting, the density grows in time during the simulation, whereas iterative shifting is able to keep it bounded. We see the error is growing a bit, and then iterative shifting is activated and the error goes down. And this is confirmed by the plot of the L2 norm of the pressure error. This dashed line is for regular efficient shifting, and the continuous line is iterative shifting. Okay, and if we do a convergence analysis on the pressure field for the 2D vortex test case, we see that the iterative shifting is able to produce results that are 2 orders of magnitude more accurate than regular efficient shifting. Okay, is this the end of the story? For today, yes, but not quite. We submitted an abstract for SPHERIC 2021 on this, and so you will have more news at SPHERIC 2021 if the abstract will be selected, obviously, in case any reviewer is listening to this. Okay, another issue, another well-known issue of SPH or weakly compressible SPH is the fact that kinematic is correct, but pressure field is noisy. And there are many sources of noise for the pressure field. The first one is the Lagrangian character of SPH, like here, when particles are rearranging themselves, you see that pressure becomes a bit noisy. And then the second source is the fact that we are weakly compressible. So we have acoustic waves traveling in our domain. And that's related to the fact that we are simulating a weakly compressible fluid. And the third, and in my opinion, most important issue is related to the fact that as weakly compressible SPH is a centered, collocated, and explicit in time numerical scheme. So let's focus on the third and most important issue. And the most popular fix for that is the so-called delta SPH formulation. In the delta SPH formulation, there is an additional term, which is the one in red here in the continuity equation. And this term has the delta dimensionless parameter, h is the smoothing length, C0 is, okay, the speed of sound, and dA is computed like that, where psi here inside the summation depends on the specific diffusive scheme adopted. In particular, in delta SPH, the psi AB is computed like that, where you have a low order term here, rho B minus rho AI, plus or minus an high order term, which is the one in red here.
Excuse me, Renato, you're about halfway now.
Yeah, okay, perfect, thank you. Okay, and by adding this high order term, you can simulate, by adding the high order term, this CAB becomes consistent close to the free surface, and so you can simulate free surface flow without having a strange effect like the one on my left. Okay, so with delta SPH, you can get much better pressure field, as it is shown in two figures at the bottom here, whereas there is not much difference in the velocity field. So the delta SPH formulation is able to maintain all conservation properties of the original SPH scheme. And this is good news, obviously. And in my opinion, the secret of delta SPH is to introduce some upwinding in the continuity equation. So you don't have a scheme that is centered, but it becomes an upwind scheme, still explicit in time, but upwind. So the question that I ask to myself, because I'm in lockdown and I'm speaking to myself a lot lately, is if can we define a different formulation that works well as delta SPH? The answer is yes, otherwise I would not show you this derivation. And the idea is to look at the so-called Godunov SPH formulation, which where the continuity equation is discretized with this formula here, and then we manipulate this formula, this equation a bit, making it 1D like that. And then we can, if we make it 1D, projecting everything on the line that is connecting particle A and particle B, then you can use a simple 1D approximate Riemann solver to express this V bar velocity here, and which becomes like that, where this superscript R means reconstructed, and those are densities reconstructed at the particle-particle interface between A and B. And they are reconstructed in a typical finite volume, or yes, finite volume fashion, where you are introducing a generic limiter function here, which is limiting the reconstruction between A and B. And this gradient is exactly the same gradient you saw before in the original delta SPH in the PCAB formulation for the delta SPH scheme. This guy here, sorry for going back. This one here is exactly the same. So basically, making the long story short, and if you want to know the details, those things are published in a paper on computer and fluids, the one mentioned here. If you use this formulation for PCAB, where there is no delta parameter, then you are using a delta SPH formulation, which is identical to the Godunov SPH formulation, at least for the continuity equation. But it's identical, but as you can see here, you don't have any delta parameter, and dissipation is automatically and locally controlled by the fact that we introduced a limiter function in the reconstructed value, in the reconstructed densities here. Okay, enough for the theory. Let's have a look at the results. Here, this is my favorite test case, very exciting, still water. And so you see how the two delta SPH formulation compares with the original weakly compressible SPH without any additional term in the continuity equation. Clearly, the noise in the pressure is reduced a lot, with the advantage that in the Godunov SPH formulation, there is no delta parameter. Another test case, less exciting than still water, which is jet impinging a flat surface, run with the new delta SPH formulation. I'm showing here the non-dimensional pressure movie. Everything is quite smooth and stable. And this is confirmed if we look at the pressure profile along the flat surface and at the pressure at stagnation point for different resolutions. This is somehow showing you that we are converging, and this is showing you that we are producing results that are as good as the original delta SPH scheme, if not more accurate, at least in this part of the domain. an alternative formulation for the psi here, which is something you can add to your code in no more than 10 lines. And the fact that you can use just 10 lines of code to do this doesn't mean that you can do it quickly if you are working with George in particular, because this took us 2 years to develop. In any case, so the idea is to delete the high order terms from the original formulation and substitute the total density here in the low order term with the what we call dynamic density. Dynamic density is computed as total density minus hydrostatic density. And details are here published in this paper, Vortex et al. 2019. Okay, so this formulation is 2 to 3 times faster than the original delta SPH formulation, and it has almost no overhead compared to the original SPH simulation, where there is no additional term in the continuity equation. And this works well for gravity-dominated flow. And this is an example of a gravity-dominated flow, wave propagation. We were able to simulate wave propagation for 150 periods. And this is the pressure field. You can see that it's quite smooth. Okay, enough for the first grand challenge. I think that future works on this grand challenge are related to the fact that we need to have an SPH scheme that is stable and it has a minimal numerical diffusion and no artificial viscosity parameter to switch. Then also we need to have an SPH scheme that is that shows high order convergence, even retaining the Lagrangian property of the original scheme. And then we need also to demonstrate or to show that our scheme is stable and convergent also for free surface and boundaries. And then also, but this is an issue more for mathematicians, we need to prove that SPH is converging theoretically. Although I have to say that last point has been addressed by in this paper here. Okay, second grand challenge, adaptivity. Nathan, how much time do I have? No, you're on mute.
About 13 minutes, Renato.
Okay. So adaptivity is defined as the ability to discretize the domain with particles of different size, as you probably already know. Why do we need adaptivity in SPH? Well, because SPH with uniform resolution is quite expensive computationally. For example, you can look at this simulation here where we needed 62 hours of computational time to simulate 21 minutes of physical time. And the resolution we were using was not ideal, I have to say, because 5 meters for this, maybe it's not enough. So people have looked at it, obviously, in the past. First ideas was related to using remeshing in SPH. And then some other authors tried to add static refinement, meaning they were trying to initialize the domain with particles with different size at the beginning of the simulation, and then they were not changing the size of the particles during the actual simulation. Finally, recently, or in the last, I don't know, 8 years, dynamic refinement came, meaning that we try to change dynamically during the simulation the size of our particles in our domain in order to change the resolution, both increasing resolution and decreasing it. So if you have particles with different size, the first thing you need to introduce is a weakly compressible, in our case, formulation where you can handle particles which have a different smoothing length. And the formulation we derived is this one. And it is derived variation starting from the variational principle and assuming that the divergence of the velocity is discretized using a scatter formulation. Scatter formulation means that inside the kernel here, you have the smoothing length of particle J. And because we are starting from this and using the variational principle, we don't have any other degrees of freedom. And we do the math and we end up with this formulation that is shown here, where you are for example, in the momentum equation, you have two different gradients of the kernel. The gradient of the kernel computed with Hj and the gradient of the kernel computed with Hi. Okay, how do we increase the particle resolution? Well, we do it by particle splitting. So the key idea is to split one particle into m daughters. Obviously, you have to define all the physical quantities related to the daughters, and you want to conserve all relevant physical quantities. First thing you have to choose is the number of daughter particles. Ideally, in 2D, you want to split one particle into 4 because then you are, doubling your resolution. But that's not a very good idea. I'll show you why in a minute. And the second thing we want to do is to reduce our degrees of freedom. And the third idea we are applying is to compute the mass distribution of the daughter particles by minimizing the density error. What do I mean with reducing the degrees of freedom? Well, it means that the splitting is controlled only by 3 parameters, which are the number of daughters n, and then there is an epsilon parameter, which is controlling the relative position of the daughters. And then there is an alpha parameter to control the relative smoothing length of the daughters. No more than that. And then, again, starting from a scatter interpolation. And please note that here, when we are trying to minimize the density error, we are using exactly the same scatter approximation I was using in the formulation I derived, and that's not done by chance. So how do we minimize the density error? Well, we minimize, to be precise, we minimize the global density error, which is defined as like that, where here E is the difference between density before and after the splitting. And then you do some algebra, you end up with this minimum problem with this constraint, and this constraint is related to the fact that you want to conserve mass. You solve it, and you you end up with your lambdas, which are the relative masses of the daughters. So if you do it for an hexagonal stencil, which is the best stencil you can use in 2D, you end up with this plot for the minimum density error. And so it means that the density error is negligible in this region here. And so you want to choose the minimum value for alpha. So alpha can be, I don't know, 0.75 or something like that. Here there is an example of a simulation with 2 levels of splitting and coalescing of flow past the cylinder. If we move to 3D, and we have a look at the same plot for the cube, we notice that the only region where the density error is negligible is this one, where alpha is 0.9. Whereas if we use, for example, the icosahedron, we notice that there is a much larger region where the density error is small, and so we can push alpha back to 0.75. And so we can conclude that the best stencil in 3D is the cube, is not the cube, sorry, is not the cube, because if you want to use a cube, then you have to use a value of alpha of 0.9, which means that a lot of neighbors which means that you are introducing an SPH simulation with a lot of neighbors in your high resolution zones. And so you are killing the efficiency of your numerical scheme. A much better choice, as I showed you before, is the icosahedron, where you can reduce alpha to 0.75. The dodecahedron is good as well, but since it has more daughters, because the dodecahedron has 20 vertices, in my opinion, the icosahedron is the best one, or the one to choose in 2D. Okay, coalescing very quickly. How do we coalesce particles to reduce the resolution? We do it in pairs. And by enforcing mass and momentum conservation, we obtain the position of the new particles and his velocity. And we compute the smoothing length of the new particles by enforcing zero density error. Okay, here you can see, again, super exciting still water simulations for 3 different levels of splitting, no splitting, 1 level, 2 levels. And this is a movie that is showing the pressure field. If we look at the pressure distribution, we see that with delta term in our formulation, pressure becomes very close to the analytical solution. And the most important thing is that you don't see any problem where you are changing the resolution inside your domain. Another simulation I wanted to show you is a dam break flow with variable resolution. You see here the movie particles are colored with their masses. And here close to the obstacle, we created an high resolution region. Okay, here we are comparing both water height measured at some gauges and the pressure measured on the obstacle. And the results were in agreement with the experimental data for this test case. And in terms of efficiency, the theoretical efficiency we could have achieved was 4, because the ratio between the number of particles with and without a variable resolution is 4. But due to the several overheads we had to introduce in the code to handle splitting and coalescing, the speed up was reduced to around 2, both in the CPU and GPU version of DualSPHysics. The final issue, if I have time, do I have time, Nathan, or not? Okay, the final issue I want to address here is related to the fact that in what I showed you so far, I was able to identify regions where high resolution was needed before the beginning of the simulation. But in real or complex problems, the truth is that we don't know a priori where high resolution is necessary. So the advisor, the old guy is the advisor, say that the idea is to control spatial resolution using a measure of the interpolation error, obviously. But then the PhD student is wondering, okay, but what is a good measure of the SPH interpolation error? Okay, so if we go back to the basic theory of SPH, we know that an SPH interpolation of an arbitrary field quantity F is first order consistent when those 2 conditions are fulfilled. Okay, those are the so-called 0 and first order moment. And similarly, looking at the derivative of a scalar function f, we have those other conditions here. And please note that those conditions are never fulfilled by a normal SPH interpolation if you are using an irregular particle distribution like the one you have in a real SPH simulation. Not only that, but the higher is the error on the moments, the less accurate is your SPH interpolation. Keeping those basic concepts in mind, we used the so-called consistency order matrix of SPH interpolation, defined like that. And we observe that if this matrix is equivalent to the identity matrix, then the SPH interpolation is first order accurate. So we thought that a good measure of the error produced by your SPH is the difference between the determinant of the C matrix and 1, which would be the determinant of your identity matrix. Okay, then we are not using exactly this in our solver. We are using the change of this in time, and we smooth it a bit, but this is really the key idea of what we are trying to do to automatically control the resolution in our simulation. Okay, here there is an example. We are simulating the 2D dam break of Iannozzi et al. And here I'm showing you where our criteria is identifying region where you need more resolution, basically, which would be this one and that one. And here you see how the criteria is introducing splitting in the simulation, because the red particles here, the red particles here are the new particles that are created by the splitting, automatically controlled by the criteria I was showing you before. Okay, this I skip it. Okay, and by doing that, we were able to reduce by 1/3 the simulation time in comparison with a simulation where we were using uniform high resolution everywhere. Okay, so to conclude, what are the future challenges for adaptivity? Well, the first one is to be able to create a full multi-scale simulations where you are able to change your resolution by, I don't know, 2, 3, 4 order of magnitudes. I don't know, for example, from millimeters to meters or something like that. And then second grand challenge is to produce, to keep the error minimum in all your physical quantities when you are varying the resolution of your particles. Third challenge is adjust particle resolution to ensure a predefined level of error. And then obviously you have the issue of being consistent and converging with variable resolution. And then you have the obviously HPG issue. How do you code efficiently this for a parallel code? And then obviously multi-phase. Okay, that's the end of my presentation. But before ending, let me say thank you very much to all those guys here. Some pictures are quite old, but at least they all have ears. Well, almost all of them, not Peter. So thank you very much.
Thank you, Renato. That was wonderful.